Welcome to another episode of Peep, an EIP dedicated series where we discuss improvement proposals, understand their importance, and also talk about how to improve the current process. I'm your host, Pooja Ranjan, and we are joined by William Schaub and Brent Alsop from the Ethereum Cat Herders. Today's topic is potential direction for new EIPs. And our guest is a long-time EIP editor who has authored some very useful EIPs and is also the founder of ENS. No prizes for guessing here. Please welcome Nick Johnson. Welcome to the show, Nick. Excited to have you and curious to know about your journey with Ethereum. So please take it away.
Thank you. So I've been involved with Ethereum since, I believe it was 2017, when I joined the Ethereum Foundation, working initially on Swarm and then on Go Ethereum as a core developer. Sort of started authoring EIPs almost from day one. I have a deep interest in building technical standards and infrastructure that other developers can use. So worked on that pretty much as soon as I had the opportunity to. And then since the EIP process was in a bit of a bind at the time, took over as an EIP editor for a while and helped try and sort of unstick it a bit. Started some of the process that's still continuing with separating out EIP standardization from hard fork determination. And I've sort of been interested in the process since then, but my work with ENS has taken me sort of away from having a lot of time to spend on standardization efforts. Nevertheless, I'm, I would say, fairly knowledgeable about the EVM and deeply interested in improving it and other things around the ecosystem, but I have a particular interest in the virtual machine.
Cool. So I definitely want to give a little bit of a preface here that I am not a core developer myself. I have, I would say, casual knowledge of a bunch of things about the EVM. I'm definitely interested in diving a bit deeper. But I guess to a large degree, I just want to give the caveat that I'm attempting to sound knowledgeable here, and I can only hope that I do a good job. One of the reasons why we reached out to you is because we've noticed that you've tweeted here and there about EVM shortcomings. And I think it's important for all of us in the ecosystem to realize what the shortcomings of the EVM are. And I think it's also a good ground for people who are looking for a vector that they might be able to improve the existing infrastructure to start looking at the problems and the shortcomings that we have now. I'm sure that some of these are more easily addressed than others in terms of backwards compatibility and also in terms of how much we can change the entire infrastructure of the EVM. But I did want to sort of use this opportunity to focus, I guess, on some of the quirks and interesting design choices that went into the EVM. So if there's anything in particular that you would want to start off with, then feel free to jump into it.
I guess a sort of a broad overview of the structure of the EVM is probably warranted briefly. And
great idea, yeah.
The EVM is more or less what you'd get if you gave a third-year comp sci student the assignment to design a virtual machine that was as straightforward and easy to implement as possible. So it has a number of advantages in that along those lines. It's very easy to write an EVM interpreter or execution engine, and this is because it's been designed with sort of maximal conceptual simplicity in mind. Unfortunately, much as with the third-year comp sci student, there isn't a lot of practical experience applied, and so there's a lot of things that are done inefficiently or are done with less sort of attention to the implementation details and the, oh dear, is my video cut out again?
Your audio is still good though, we can hear you.
Okay, less attention to the implementation details than is perhaps warranted. And the result is that efficiency is a serious issue with Ethereum. And that also, the design also impacts things such as the ability to statically analyze contracts, things such as that. So there's definitely a lot of room for improvement. Some of it we're stuck with because it would break backwards compatibility too badly. Others are, we can potentially remedy with backwards compatible improvements.
Cool. So if I could maybe take something that you said there, I think that you mentioned two different metrics that we could sort of measure the EVM by. One is the conceptual simplicity, which you said is really maximized in a lot of ways. Another is the efficiency. Another one that I see brought up every now and then is the not composability, the ease of understanding. Like sort of, I don't think scrutability is a word, but if it would be, I think that's what I'm looking for. That just an understandable and easy to parse choices in the actual construction. So let's try and dive into that a bit. One of the things I think on any list of like, EVM critiques, I think almost always the first one is 256 byte words. Do you think that that sort of belongs in that space? What problems do we have because the EVM only reads 256 byte words? And is there any way to do anything about that?
Yeah, that would sort of be the first example I would reach for when talking about the EVM's choice of conceptual simplicity over practicality. It's the reason it was picked basically is because some operations in the EVM need to be done on 256-bit operands. So public keys, addresses, and so forth. Although, addresses are 160 bits, but, close enough. Hashes, of course, are another very common example. And so the reasoning and the sort of thing that you'd see in a model VM is, well, some of our operands need to be this long. If we make all of our operands this long, then we minimize the size of the instruction set. We have the simplest structure possible. Whereas if we had multiple options, then you would need multiple opcodes for different lengths of operation, and your instruction set gets more complicated, your VM architecture gets more complicated. In retrospect, I think that would have been the correct thing to do. Or, for instance, to push all of those longer operations to memory rather than the execution stack. And the result is that even very ordinary operations like addition and multiplication of small numbers, like indexing arrays, require words that are 4 times the size of what a common machine actually implements. And so in order to add 1 plus 1, your machine in a naive implementation under the hood is adding up 4 separate numbers and incurring many times the overhead that's necessary. So I think that's a perfect example. It's slightly more difficult to fix because although you could implement diverse word sizes and so on, you would have to significantly expand the instruction set. You'd need to change a lot of things around. And it's unclear to me whether that would be the best way to do it. But I think it also points at the general sort of architecture of the EVM in that it was chosen that all items on the stack would have just a single type. They would all be 256-bit words, which is both simple and mirrors how you'd implement something in hardware. But if you look at other intermediate language VMs, such as the CLR, the Common Language Runtime for .NET, or the JVM, they have stacks that take objects, basically, and they can take multiple different operand types, and it would be less of a blow-up of instruction set and complexity to say you can push a 32-bit word or you can push a 256-bit hash, and here are the operands defined on that.
Sorry, I just lost my train of thought there for a second. The intermediate languages that we see being implemented, like, Yule or something like that, do they have any way of working around this?
Not really. I mean, they can and do define smaller operands, which make their reasoning easier and allow them to do things like, overflow checking on smaller types, on things like potentially packing things together into structs for storage. But none of that information makes it through to the VM, so it doesn't benefit the VM implementers. So it is possible to write a VM that optimizes things and avoids operate on 256-bit words when you know both the operands and the product will fit in the smaller space, but you have to do it at runtime. And in fact, your ability to do it at runtime is also hampered by the fact that the EVM is very difficult to statically analyze because all jumps are dynamic. And so as a result, you can't go ahead and do all of these optimizations ahead of time. You have to do them on the fly.
I definitely did want to get into the jumps later. Debating if I should seg you into jumps now or keep on the words for a second. I think I am going to stay on the. Wow, I am like not with it. I'm like losing my train of thought left, right, and center. I am going to jump onto the jumps. I think there we go, an EVM style jump. A lot of I see a lot of complaints about the way that the EVM jumps around. You've mentioned a couple of times that it makes the EVM difficult to statically analyze. Could you explain a little bit about that? About, I guess, maybe taking a step back to explain what static analysis is, and then how the EVM's implementation of jumps make that hard.
Sure. Sorry about all the video issues. I don't know whether this is any better.
So far, so good.
So one of the goals of a VM, or at least potential goals, is making it easy to statically analyze a program. And what that means is take the program and do some sort of analysis on it that tells you something about it. So for instance, a really useful analysis might be if you could determine statically that this particular operation will never overflow a 64-bit word, for instance. And you could tell that by saying, by establishing bounds on the inputs. You could say, well, I know that this input comes from here and it's limited to this size, and I know that this input is this constant 6, and I know that 6 times this can never be more than a 64-bit word, or something like that. And in many cases, static analysis it gives you 3 answers: yes, no, or maybe. Because of Turing completeness, you can't always get a complete answer. But even just being able to analyze the cases where the answer is yes allows you to implement optimizations and so forth. And so that also allows you to do things such as determining whether certain code is reachable or under which circumstances it's reachable. It's useful not just for runtime optimization, but also for analyzing programs for correctness and so forth. If you can statically analyze a program, then you can more easily determine properties like whether a particular invariant holds, whether, for instance, a token will always preserve the sum of its balances and things like that. Some of these things are difficult to do even in VMs that are designed for this, but the EVM is particularly hostile to this. And the reason for this is that there are 2 jump opcodes in the VM that allow you to jump to another location in the code. And both of them take the argument for where to jump from the stack. And that means that, in principle, the argument for where to jump can be the result of another computation. So if you try and statically analyze the VM, your circumstances in which you can do this are much more limited, because you have to be able to determine what this jump location is statically. And actually doing that in the first place is extremely difficult. So typical basic control flow analysis in a VM where the jump locations are determined directly from the code is a reasonably straightforward process. But doing it in the EVM basically involves sort of pseudo executing all the code to try and figure out where your operands are coming from. And because of the stack-based nature of it, the opcode for where to jump could well have been inserted in the stack a long way back, because they had to do a bunch of other intermediate things first and calculate results and so forth. So it's very difficult. And there are efforts to remedy this in a mostly backwards compatible way. Greg Colvin has submitted some proposals for new jump opcodes, and the idea would be that old programs would remain difficult to analyze, but new programs could use these jump opcodes and therefore be easier to analyze going forward.
Interesting. In other VMs in general, how do they get around that issue? They just don't let you dynamically declare a new jump spot later in a stack?
Precisely. Yeah, so this is another example of the conceptual simplicity of the EVM. There's a total of 1 class of opcode that has arguments, and that's the push opcodes. So you have push 1, which takes the next 1 byte, and push 2, which takes the next 2 bytes, and so on. And they grab the next n bytes from the bytecode and shove them on the stack. The jump opcode, like every other type of opcode, doesn't take anything from the bytecode directly. It only takes it from the stack. So if you want to jump, you do say push 1 and then the 1 byte offset and then jump. What other VMs do is that the jump opcode itself takes the argument directly from the bytecode, and that means it can't change, and that means when you're going through and analyzing it, you know exactly where that can possibly jump to.
Very interesting. I did remember what I had been thinking of asking before, which is when we see inefficiencies in the EVM, let's say the fact that we're using 256-bit words and we can't chop them, the EVM doesn't recognize something smaller than that. Does the resulting inefficiency translate itself in some way as an extra gas cost?
Not as an extra gas cost, but rather, well, so that's not quite true. Yes, some operations cost more gas than they would if they were more efficient, simply because the gas costs reflect the actual cost of execution. But also the general inefficiency, particularly when it comes to global things like operating on 256-bit words, effectively just inflates the cost of gas globally and decreases the maximum gas limit that Ethereum could afford. So if the EVM had been implemented with 64-bit words, we could potentially fit, say, as much as twice as many units of gas in a block. At a random guess, it may well be more than that, just because of the sheer overhead of having to evaluate all of these large operands every single computation step.
Yeah, I think that actually ends up being partially a computer science question and partially an economics question, because if we had more efficiencies, so then it doesn't necessarily, like, it could be that the gas price for a smaller operation that can now be performed might very well be smaller. But like you're saying, the resulting effect is just that more gets packed in.
Yes. And there's a phenomenon in civic planning where you expand roads and the traffic expands to fill them. And
Yes.
it feels like the same sort of thing here.
Okay. So that's a bit on word size and on jumps. What about, I think stateless is covering this, but another thing that I see brought up quite a bit is the Merkle-Patricia tree or trie. In terms of the trie storage, do you see that as also like a inefficiency? Also, I mean, I see that James is here. It could be, you could comment if stateless is I believe stateless is working on another trie structure. So it could be this is something that's actually already under development, but I was wondering if you could talk to that a bit.
Me or James?
I guess, James, if you could mention if stateless is talking about it, but otherwise, Nick.
I know that they're working on converting to a binary tree at some point, or that's in the roadmap of the moving to the data layer of statelessness. That's all I know.
All right, cool. Nick, would you mind talking to that, like what the Patricia trie is, and like what the big inefficiency there is?
Yeah, absolutely. So the Merkle-Patricia trie is in an interesting position because it's too narrow, so too small a branching factor for efficient disk access, but it's too bushy, like too high a branching factor for efficient proofs. So if you're wanting to send a proof over the wire, like with stateless Ethereum, ideally you want a binary tree because that way you only have to provide the hash of one other internal node with every level of your Merkle proof. This is assuming we're using Merkle proofs. And so with Ethereum's current Merkle-Patricia trie, you have up to 15 other internal node hashes with every level of the trie. So the trie is a lot shallower, but you end up having to spend a lot of effort encoding all of these other hashes. In practice, it's usually a lower branching factor than that because you don't have every branch at every level, but it still results in a lot of wasted overhead. When it comes to disk access, though, there's the idea of the delay bandwidth product, which is effectively the number of milliseconds it takes you to do a disk query times the theoretical throughput of your disk. And if you're making very small reads, then you're spending most of your time waiting for the data waiting for the query to happen and the response to come back, and your bandwidth is sitting idle. And if your blocks are really big, then you're reading a whole lot of data that you don't need. So the sweet spot is somewhere in the middle there, where you spend about half your time waiting for the query and about half your time reading data. And for modern disks, and in fact for quite a while now, really, that product is somewhere in the region of like 128K to a megabyte. In contrast, a Merkle-Patricia trie node is on the region of like 128 to 256 bytes. So what we should be doing is, if we wanted efficient disk storage, and that would reduce the number of reads you have to do to read a single value off disk, which would correspondingly decrease the cost of an ESLoad or an ESStore, you would want a tree that was much, much bushier. And if you want efficient proofs, you want a tree that's much, much narrower. And there is a sort of a solution here, which is that you store on disk the aggregation of several levels of trinode together as a single unit. But then when you transmit them, you send them as individual nodes, just parts of the block. So you read out an entire very large, very bushy sort of subtree as a single read operation, and then pick out the bits you need. Unfortunately, doing that in the backwards compatible on ETH 1.0 is difficult, because the wire protocol for synchronizing nodes has a primitive which is read a trinode from another Ethereum node. Great overloading of terms here. And so if you try and write a more efficient Ethereum node that stores things that way, it has no way to fetch nodes that are internal to one of your sort of aggregated blocks, and it breaks the sync protocol. And in fact, this is kind of what Parity did back in the day with warp sync and so on. A warp sync node was actually unable to serve up some of the internal nodes of the trie, and that didn't become a big problem because Parity was only ever a minority part of the network. The sort of Geth picked up the slack, but it's an ongoing problem with any trying to do that sort of optimization.
Very interesting. You mentioned before, just getting back to the conversation we started about the word size and the memory, that the EVM makes some interesting choices with regards to what goes on the stack, what's in memory, what's persistent, what's not. Could you talk about that?
Yeah, and it was sort of, I have a short little list of things that could do with future improvement and are actually practical, and this was near the top of it. It's so the EVM has the execution stack because it's a stack-based virtual machine, and all of the opcodes take arguments from the stack. And it has some stack manipulation opcodes which allow you to swap elements around or duplicate elements from the stack. But the intention of the EVM designers clearly was that this is a stack-based machine and this is for evaluation, and that if you're building a higher level language, typically you would store the actual variables in memory, and then you would load them from memory and save them to memory as needed. And if you have an optimizing compiler, then it can identify, oh, some of the time we don't really need to store this in memory, it can fit on the stack, but that's an optimization you sort of pull out, just like on a more traditional architecture, pulling stuff out to registers instead of memory. All of this is somewhat handicapped, though, by the fact that the EVM's memory space is a linear area starting at 0. It has a 256-bit address space, but when you write to it, you get charged based on the furthest address from 0 that you're writing to. So if you wrote a single word of data to memory 128K in, you're charged for allocating the whole 128K of memory, which is quite expensive in gas terms.
Ouch.
And so if you look at the traditional way of building a compiler, compilers are typically structured with the stack and the heap, confusingly more overloading. In this case, the stack is the stack of variables, not the stack of the execution stack like the EVM. And the heap is for things that are dynamically allocated, like where you call new in C or Java or whatever. And what they do is they stick them at opposite ends of the memory address space, and they grow towards each other as they fill up. And that's a very easy way to build it because you generally don't have to worry about the two running into each other until you've literally run out of memory. And in the case of the EVM, if it supported this, you wouldn't, because you've got a 256-bit address space. But because the EVM charges based on the total length of memory consumed, this compiler structure is impractical. And so when Solidity was written, for instance, they decided to put all of the variables, all of the local variables on the evaluation stack rather than putting them in memory, because that way you don't have this whole issue of them sort of being interleaved with stuff that's been dynamically allocated and so forth. The flip side is that then you have the whole stack too deep, please try removing some local variables error in Solidity, which is a bit of a nightmare. So here's somewhere where someone who was determined could actually make a difference. I think, and I'm not aware of any big barriers to this, it would be quite practical to write an EIP that changes the gas accounting for memory to use a page table structure. So with a page table structure, you would be charged for each page of memory you use. Even if you only write 1 byte to it, say you use 4K pages, you get charged for a 4K page, but it doesn't matter where that is. So you could allocate a 4K page at address 0, or you could allocate it at, address 2 to the 255 minus 1. And each time you just get charged for 1 page. And that would allow writing compilers that take this more typical architecture and structure heap and stack at opposite ends. And that would make it possible to write sort of better and more versatile compilers. And the best thing is, for programs that were written before this, they would simply be charged what they are now or less, because they would be charged based on just using the first pages of memory.
That is super interesting. So basically what an EIP like that would do is, instead of using the current the current structure for charging gas for putting things on the stack, which doesn't look at how much you're putting on, it looks at the location of the information that's put and charges for the entirety of the stack up to that location. This would be looking at the actual information pushed to stack. Is that roughly correct?
So we're talking about charging for memory rather than the evaluation stack. The evaluation stack is limited to 1024 slots, but it's not directly charged for. But at the moment, memory is charged based on the length you use from 0 up to the last byte that's non-zero. And with this, instead, it would be charged in pages.
Very interesting. And like you said, that gives the ability to create a simultaneous stack and heap, which allows, and that in turn, how does, so I'm realizing now that I think I've lost the thread of it. How does having a stack and a heap allow us to be more versatile?
So in a typical programming, just to disambiguate, we're talking here about a variable stack, so a stack of local variables. So if you look at it, say, how C implements it, for instance, when you have a local variable, the compiler says, okay, the next byte after the beginning of this function's frame, which is where the sort of the bit of memory that belongs to this function starts, is going to be this first variable, and then the next variable, and so on. And then when you when that function calls another function, it goes, okay, we'll move the frame up here, and now we'll start writing new variables up here, and so on. And when it returns, it goes, okay, we'll move it down here, and all this memory is now free for the next function call. And at the same time, at the opposite end of memory, you have the heap, and the heap stores things that were dynamically allocated using functions like new and malloc, because they can outlast the function call that they were called in. You can call a function which allocates something and passes it back to you, which means it can't be put on the stack, because if it was, it would go away as soon as the function returned. Okay. So that's kind of like a semi-unstructured area up at the top of memory that has all of these blobs that, can be held more or less indefinitely, and their lifetime is, different for each one. The problem with trying to do all of this, if you put it all starting at the bottom, is you'd have sort of, function stack frame here with a bunch of variables, and then you've got this dynamically allocated thing, and then I guess you have to put the next function up here, and then when this returns, you can go down here, but then this block where you dynamically allocated this thing is still used. And so when you make more function calls, you butt up against it, and you somehow have to know this is here and avoid it, and it's a nightmare. It's effectively impossible to do. So what compilers like Solidity have done is they've said, okay, we're just not going to have a local variable stack at all in memory. We're just going to store everything in the EVM's evaluation stack and accept the limitations that come from that. I mean, my personal opinion is that probably a smart contract programming language shouldn't really support dynamic allocation, and it should only have a local variable stack in memory, because dynamic allocation is generally avoided in embedded systems, which the EVM is pretty close to in many ways, because it causes trouble with scope and with with a whole variety of things really. But that ship has sailed, and they made the reasonable choice to support it, but they're somewhat handicapped by the current EVM design. The nice thing is that this would actually be, I think, a relatively easy accounting change, and a slightly less easy but still not terribly difficult structure change to how memory is stored in EVM implementations, that would then enable a whole lot of new use cases and better compilers.
Interesting. So, and in short, then basically what we'd be able to do is we'd be able to differentiate more easily between more ephemeral data and data that needs to stick around for longer, without running into these nightmares of just knowing where what's still being used, what's not being used, fitting new information around it.
Yeah, the really short version is like you could do away with the Solidity's too many local variables era, which I'm sure would be attractive to a lot of people, myself included.
Indeed.
Hey, so quick question, or not really necessarily. Well, what I'm interested in is, what do you see as like the biggest thing holding back at the growth of Ethereum and the scalability of Ethereum, and where do you see a solution in the future to that?
That's pretty broad, I guess. It's I think it's outside the EVM really. The issue holding back the growth of Ethereum really is capacity, and so that comes down to sharding and other efforts to improve that. I've never been convinced that sharding as like that sort of homogeneous sharding where you can migrate things between shards and every shard is effectively the same and so on is ever a practical option. So you're sort of left with heterogeneous sharding, in which case you basically have a whole bunch of different mini Ethereums that can all communicate, and that runs into problems where everybody wants to be on the one that everybody else is on, so your sharding becomes less effective. Or systems like sidechains and so forth. And I think that at this point that roll-ups and sidechains are probably the most practical option, because you can effectively have your sort of application chain. You can run an optimism instance or whatever, and then you just acknowledge that everything not tightly associated with your project is going to have to do some asynchronous communication between it. So I think, ultimately the short answer is scalability is the biggest issue, and roll-ups and systems like it are going to be the easiest solution.
Yeah, I hadn't heard of the role. So for the sharding, I remember you mentioned something about like it's almost like an asynchronous process. Would you say that the current way that the EVM is built is like comparable to say like a single threaded process, and then the sharding would be multi-threaded?
So the current EVM is definitely directly analogous to a single threaded process. I think sharding is more like multiple processes than multiple threads, because they can't directly communicate with each other except by passing messages. And in the case of any practical either sharding or roll-up system, those messages have to be asynchronous, and that your calling process can't hang around and wait for the result to come back.
And why would people want to be on the most used shard?
So in the case, I think where you have multiple identical shards, the attraction is that if you're on the same shard as, say, Uniswap, then you can make synchronous calls to Uniswap and get the result back, and that's simpler and more efficient, and also faster in the sense that you can respond to the data it returns in the very same block. But if you're on another shard, then you have to send a message and then wait potentially several blocks for the response, which is both more complicated to program with, and if you're trying to do something like arbitrage, it just doesn't work. So you have this perverse incentive to all group together on the same place, and potentially you end up with a few sort of hot shards and a whole bunch of ghost shards that are little used. And so your actual scalability is much worse than your theoretical scalability.
Would you say that a major, one, say, like fanatical or fantastical solution would be a framework where it's like asynchronous processes are handled, like are kind of the basis of the functionality? So the benefit of being synchronous on the same shard, for example, would be outweighed by the benefit of multiple shards?
I was kind of hoping you'd ask that, actually, because I think asynchronous communicating processes is a really interesting model, and it would have been a really good candidate for Ethereum from day one. I think it would be really neat. I'm unsure how practical it would be to retrofit, in the sense that, I mean, yes, we can afford to break some backwards compatibility moving to ETH 2.0, you know, as long as there's an option to run 1.0 stuff. But I think that the programming model might be so different from the current stuff that we would lose a lot of our tooling and so forth. And I think that that might be enough to discourage people from trying it.
Thank you.
My pleasure.
It's interesting, maybe moving on to a slightly different subject. Researching a bit, when I was looking at different critiques of the EVM, I found critiques saying that the bytecode needs to be more human readable. Then I also found critiques that the bytecode needs to be more concise. So I was wondering if you had any specific opinions about the way that the EVM compiles its bytecode.
Yeah, stack-based machines, I think, generally tend to be reasonably concise, except insofar as sometimes they require the whole push something and then do something with the thing you've pushed, which can give a slight expansion of size. I think in general they tend to be reasonably concise, you know, at least by my standards. There definitely can be less readable because you've got a lot less locality in terms of where your references are coming from. You know, you see this add opcode and you know it takes the top two arguments from the stack, but tracing back where those two arguments came from is a whole hassle all on its own, complicated by how difficult the EVM is to statically analyze. So other VM models like register-based VMs are definitely more human readable if you're looking at the text form of the VM bytecode. But if the EVM was more statically analyzable, we could write tools that make them just about equally easy to read. You know, you could annotate your add opcode in the disassembly with you know, arrows or indicators or variable names pointing to where those arguments come from, which would make it much easier to follow.
I understand. Interesting. Human readability on these things definitely became a big topic this week with the whole Nexus Mutual incident, and people, I think, reviewing hardware wallets and how to maximize security with them. So it's good to hear about that also. The last topic on the EVM, I wanted to ask you about the logging system on the EVMs. I've heard a lot of grumbling about the way logging is set up, but I don't have a lot of context about what a better setup might be. Certainly from the perspective of a developer, I know that event scraping can be amazingly difficult. I mean, we're used to having APIs where we can just fetch 50 and paginate over things. And it becomes much more difficult with event queries to do something like that. Is that an inherent weakness in the way that the logs are set up?
So I might be a bit disappointing here in that I actually think that the event logging system is one of the best designed bits of the EVM. The original vision and which a lot of contracts actually implement is that when something changes in your internal state that is relevant, you log that event in such a way that an external process that's replaying all of those events can reconstruct your internal state, or at least the bits that are relevant to external observers. So if you take the example of tokens, every time you emit a balance change, then every time your balance changes, you emit an event. And that means an external process can sum up all of those balance changes and arrive at the ledger of all the current balances. In practice, this isn't actually true because ERC20 has some serious flaws in terms of what it specified should be logged and when. But that's the idea, and I think it's actually a really sound one. Indexing events is difficult for nodes because they operate in a sort of a time series fashion, receiving blocks and indexing them. But often we want to fetch long past blocks. And part of that could be improved with better indexing on the nodes. But it's also a fundamentally difficult issue is how do you index data when you don't know what the query pattern is going to be? We have indexed fields, but that's about the most flexibility we have. And yet nodes have to somehow store all of this data in a way that's efficiently retrievable when they don't know their applications and they don't know what their users are going to want. And they're also constrained in terms of the processing resources they can devote to it without opening themselves up to DOS attacks. I think that we can certainly do things like TurboGeth have done to significantly improve how events are stored and indexed and fetched, but that ultimately the solution is always going to be something like the graph, where you have a process that plays back all of those events off chain and constructs a database that is application specific, because often your queries on an application are going to be non-temporal. They're going to be, give me the balance of the top 10 accounts or something, which would always fundamentally require replaying and summing up every single event, which is just not practical. So you have to maintain these application-specific databases that index stuff that's relevant to that particular application, which nobody can know on a sort of a node designer certainly can't know what that's going to look like.
Very interesting. Listen, it's definitely not a disappointment to hear that something is architected well. I think that about wraps up my protocol layer questions. I know that Pooja was interested in asking you also about your role as a EIP editor and the EIP process. So I'm going to hand things over back to the cat herder in chief.
Thank you, William. So yeah, moving on to the next section to like the EIP process section. But before that, I would like to thank William to bring Nick on the show. I mean, I have heard that it's really hard to get to you. I mean, I would like to give some credit to Twitter as well. That helps you give break time to time whenever you need. So I suppose that you're aware of the recent changes that EIP standardization process came up through. Yesterday, we released a blog documenting the process and the new statuses by one of our cat herders. It's an alien. How do you see the current process with respect to early EIP process?
So I think it helps perhaps to sort of look at where EIPs came from, and they originated from BIPs, Bitcoin Improvement Proposals, which were pretty much exclusively used to propose, well, no, sorry, that's not true. Initially designed with hard fork changes in mind, but then used for a whole lot of other standards. And I don't think they really took the effort to separate those out. And it wasn't as big of an issue for Bitcoin because they're so reluctant to fork. BIPs originated from PIPs, Python Improvement Proposals, and Python doesn't have that issue. Like every Python improvement proposal is a proposal for a change to the spec of Python. And if you accept it, if it's accepted, then it's implemented as a change to the spec. You don't have this whole thing of this is defining a standard by which we just advise you do a thing like ERC20, or this is defining like a fundamental change to the system. So in a way, we were on our own with neither precedent being very useful in terms of figuring out how to separate out these things or separate the concerns, I guess. And initially, I think the EIP process was quite messy as a result because nobody really anticipated this, becoming a thing. And as a result, there was a lot of politicizing around, how EIPs should be approved and so forth. And effectively, people saw them as a governance mechanism for what goes on the chain. So my motivation when I was acting as an editor was really to try and separate that out, to say, look, this is a technical standardization process. This is how you standardize, this is how you standardize the specification of a thing in a way that everybody can read and agree that it says the same thing. And then if you want to take that standard and say, we should implement this on the Ethereum mainnet, then that's something you should pretty much do outside the EIP process. What we've done is we've provided you with a clear spec that everybody can agree will implement the same on every node, And so I think that's been, the direction you're driving in as well now, and I think it's a really good thing, because it's really important to have good technical standardization. It makes shared engineering easier, and in fact, it just kind of makes it practical at all. And trying to conflate that with trying to decide, where to implement changes and governance of systems is a bit of a fool's errand in my mind. Sorry, I think I may have strayed from the actual question you asked.
No, that is really good to know. Like we also have joined by James. So James is presently leading the second half that you said that contains more controversy, which should go in and out, by taking a lead on network upgrade process. So I believe that this process is going to be very helpful for Ethereum as well. So talking about the categories and the EIP categories, initially we had like 3 different categories: standard, informational, and meta. I feel that standard track is the only category that is making good number of improvement proposals. Like other 2 categories, meta and informational, are underutilized. So in some cases, like we have recently observed that many people are just creating a pull request with individual DApp specific use cases and making that as an informational EIP. My question to you is, like, do you have any thoughts on what should be documented as informational EIP? For example, like any potential use cases that you would recommend people to create a pull request for?
It's a good question. I think a minimum bar probably needs to be that it is sufficiently of interest to a sufficiently broad spectrum. So if what you're standardizing is just one particular DApp's nomenclature or notation or numbers registry or something like that, you probably don't need an EIP for this. You can document it anywhere you want that is reasonably stable. I think, though, that in terms of informational EIPs specifically, we don't necessarily need parity between that, the numbers of informational EIPs and the numbers of standards track EIPs. There's always going to be some types that are a lot more specific, a lot more less of interest to the general technical developing population. So I guess my general push would be, for a lot of stuff that people want to write up as an informational EIP, consider whether you need an EIP at all in the first place. One tangential thing is, I wonder if at some point it would be useful for the EIPs process to have the equivalent of the IETF's registries, because currently we have a number of standards that require defining a registry of some kind, a mapping between numbers and allocated identifiers. And the canonical example in the wider ecosystem is SLIP44 with the coin IDs. That's not really a standard. You can define a standard, which is how to use those and encode those and so on, but the list itself, in the case of the IETF, they've quite sensibly separated that out, and they've said this is a registry, and a registry has rules for amending it. And that gets around the issue that you want your standard to be stable and eventually fixed, but you need your registry to be a thing that grows over time.
Interesting. So I have one last question on this. Please excuse me quoting you here. One of your quotes, I found that I don't cheerlead, and I'm happy to talk about Ethereum shortcoming and trade-off. So my question is here, that may lead to controversy. I do not want to, but I just want to get your opinion here. A few minutes ago, we saw some discussion on what should be there in the EIP repo. Should we have ERCs as a separate, separated from the present EIP repo? Do you have any thoughts on that?
I think that the ERC versus EIP thing originated with the whole discussion around how to handle hard forks and so forth, and that absent any consideration of trying to be a governance mechanism, there's no reason to separate out ERCs from EIPs. They're both defining standards that are technical in nature, just at slightly different levels of the stack. They're both on the same system. They both have many of the same stakeholders. I think it's fine for them to continue to coexist, as long as it's clear that when it comes to EIPs of the consensus modifying nature, that it's purely about standardizing the contents of the change.
Thank you. I think Brent has a couple of questions for you. Brent?
Yeah, just a quick question. You mentioned a lot of the core developers talk about separating out the politics from the specification, but that always seems problematic to me. And if you have a hierarchical organization, it's not problematic because the guy at the top says, thou shalt do this, and everyone does it. But if it's leaderless, like Ether is, you risk forks and all those kind of problems. But I'm interested in solving that problem. How can you do hard things like you mentioned, an asynchronous, switching to an asynchronous programming paradigm, or recovering $1 million worth of Ether that's locked up in a contract, or any that, you know, everyone wants to make that change, but it's too controversial. But I'm interested in, can we solve that problem? And we're working on a tool that I think could make that more possible. But anyway, do you have any ideas? Is there anything that you think should desperately be done to the EVM or anything that is just too controversial and we just can't do it? And because I'm looking for a pet project like that I think we could prove could be done. And so do you have anything along those lines that I could jump on board and see if we could bring it to pass?
I think the biggest things that I think are impractical are mostly because of their wide-ranging technical implications rather than because of controversy, or rather they would be controversial because the argument would be whether or not this is worth the difficulty of implementing it. So, for instance, Greg Colvin's better jump opcodes are a definite step forward in terms of static analysis, but nothing. It's still a partial measure because the real measure would be like EVM v2. Everything in EVM v2 has to use these new opcodes, and really just going back over all the decisions around the EVM that affect the ability to statically analyze them. So, if I had my dream, we would go, okay, we've sat down, we've looked at the EVM in detail. Here's a V2 that satisfies all these requirements. And, maybe we'd just do one thing. We'd make it more statically analyzable rather than also trying to fix word size. And, you want it to still resemble the EVM. And we'd go, now we're going to propose a hard fork to include support for this V2 EVM. And then later, maybe we're going to prohibit this deployment of new V1 EVMs if you want to get really controversial. But then that leads to all sorts of problems because it's effectively impossible to completely prohibit deploying old, EVM V1 code for various reasons. But I think again, the main controversy around that would be that introduces a lot of work for node developers. It introduces a lot of technical risk around new bugs and so forth. The benefits are clear, but are they worth it? Like different people will have very different opinions on that front.
Okay, cool. So probably for what I'm looking for, probably just finding $100 million worth of Ether that's locked up and just seeing if we can find up a mechanism that we can get everyone and prove that everyone's on board with a process to recover $100 million worth of Ether or something.
I can't imagine we could find $100 million worth of Ether that's locked up due to a smart contract bug. That sounds like a difficult problem all its own. No, sorry.
But there's so what's the largest? There's millions of dollars worth of Ether locked up, right?
Yes, there is. And the parity. I was thinking of the parity.
Yeah, the parity. That's the one I'm talking about.
That. Yeah, I was just being facetious, really. Sorry.
Oh, okay.
If you want to take that on as a challenge, then I'd be very interested to see how it goes. It sounds like you're talking mostly about better ways to understand community sentiment and understand when you've come to consensus, and
measure that and track it and make it possible so that you can do critically hard things like that and outcompete a hierarchy and be able to do that. But anyway, yeah, that's.
Thank you, Brent. We probably went a little over time, but I think it was totally worth it. I wanted to touch a little bit on ENS as well, but maybe we'll save it for some other time. Also, I see some proposals are there, which I think would be worth discussing. It's in some point of time. Maybe we should arrange another meeting with you, Nick, sometimes in February, March, if you are available, and we'll try to arrange that.
That would be great. Yeah.
Hopefully today's episode will be helpful for people to know about the history of EIPs and processes around, as well as the EVM section that we discussed, the thoughts that were shared today. We discussed some potential direction for new EIPs, core EIPs specifically. So viewers, if you have got a proposal and you are planning to document it, please follow the suggestions that were discussed today. And we also have an episode with Matt Gannett on writing the EIP. So if you haven't watched that and you are planning to write a proposal, it's highly recommended to watch, and it will provide you a feel of what are do's and don'ts for a very good proposal. That increases the chances of getting merged and accepted. We started this Peep and EIP series in late August this year with hopes that it will help explain core proposals under discussion, create awareness about the EIPs and ERCs, and above all, contribute to the process improvement. I'm very excited to share that it has created a distinct place in the EIP resources and is very helpful for a proposal overview. This is the last episode for 2020, but we have got quite a few interesting proposals lined up for 2021. So stay tuned with us. If you have questions, comments, and concerns about this episode or any other EIP, and I have suggestions that which proposal can be included in our show next, please leave a comment. If you like this episode, don't forget to hit like and share button. Do subscribe to Ethereum Cat Herders YouTube channel. You may find Twitter handle for today's guest and rest of the participants of this meeting in the description section below. We'll be back in January 2021 with another new proposal. Till then, keep sharing your love with Cat Herders. This is your host, Pooja Rangan, signing off. Happy holidays and a very happy New Year's. Cheers.